In the last lecture we discussed conjugate of complex number and also modulus of a complex number. Let me just recall. Any general complex number a plus I b, the conjugation, that is z bar, we defined it as a minus I b, and modulus of z we defined it as square root of a square plus b square. Now, let us see some properties of modulus. So, throughout this discussion, for this we will assume that z is of the form x plus I y, and let us just prove this. Real part of z is always less than or equal to modulus of z, as well as it is greater than or equal to minus of mod z. It is nice inequality that real part of z or modulus of a real part of z is less than or equal to mod z. So, the proof is simple. What we have, real part of z, which is x, and when we consider its square, real part of z, consider its square, that is x square, that is certainly less than or equal to x square plus y square, that is we are adding some non negative number. So, now immediately you see that whenever you have a is less than or equal to b, square root of a less than or equal to square root of b. So, this implies that real part of z is less than or equal to square root of x square plus y square. This is nothing but mod z, and what we see here, it is in fact the way we have derived, it is just the, even in the absolute sense, this will be less than or equal to mod z. So, that concludes the first proposition. Similarly, we can prove that imaginary part of z is greater than or equal to minus mod z, less than or equal to mod z. Proposition 2 is certainly it is straightforward one, that is mod z always a non negative number for all z in complex numbers, and what we need to observe is whenever modulus of z is 0, if and only if z is 0. Okay. This is basically like again which is easy to observe, because once you consider mod z equal to 0, it means it is its square is 0. So, this implies that x square plus y square, this is 0, and what we are saying is that sum of two non negative numbers are 0, that implies basically each non negative element must be 0, that is x square must be 0 as well as y square must be 0, that concludes that x equal to 0, y equal to 0. So, this is nothing but same as saying that z is a 0 element, and z is a 0 element which is basically like it follows. And what are the other simple observations? When you consider modulus of z, which is also same as minus z modulus, again it is same as mod z, which is a trivial one. Maybe I will add to this, which is basically its conjugation as well, same modulus. So, what we are basically saying is, when you take a z, then minus z you have. So, let us say this is basically x plus I y, then minus z you have minus x minus I y. So, this distance is the same as this distance. Similarly, you take its reflection about the x axis, that is z bar, modulus also same. Now, the fourth one, when you multiply z with z bar, we get mod z square. So, by definition it is clear. So, we am not basically discussing this. Let us go to the fifth one, modulus of z 1 into z 2, it will be same as mod z 1 multiplied with mod z 2. Proof is, consider mod z 1 z 2 the whole square. By the above proposition, we are getting z 1 z 2 multiplied with z 1 to z to the whole bar, and again we know the relation about the conjugation. So, the conjugation for z 1 z 2 is z 1 bar multiplied with the z 2 bar, and using the commutative law we can finally, let me just write down. So, what we have here is product with z 1 bar z 2 bar, and we get basically the associative law you could use, and then we use the further commutative law. So, you can get the mod z 1 square mod z 2 square. Okay. So, this gives the conclusion that modulus of z 1 z 2, it gives mod z 1 multiplied with mod z 2. You first take the product, take its modulus, which is same as, first take the modulus for the each complex number, then multiply it. Okay. And the sixth proposition, which is a famous or nice inequality, which is repeatedly will be used, okay, which is called triangle inequality. So, the inequality states that if you consider modulus of z 1 plus z 2, this is less than or equal to mod z 1 plus mod z 2 for every z 1 z 2 in the complex numbers. Okay. Let us try to understand this inequality, what it says. So, we have 2 points, let us say this is z 1 and let us say this is z 2, and then we can associate naturally a vector for this. So, we can visualize z 1 as a vector and z 2 as another vector. Then the sum gives the, what we basically get is, which is the diagonal for this parallelogram, that is z 1 plus z 2. So, as I mentioned in the previous lecture, modulus, it means that it is a distance between the complex number and the origin. So, modulus of z 1 plus z 2 indicates the distance between this number to the origin. Okay. So, the distance is less than or equal to distance to go to z 2, and then further you go using the vector z 1 to reach this point. So, it means like taking a distance, go first z 2 and then further use z 1 to reach here, that will be always bigger than the so it, in other words, this is the shortest distance what we are observing. Okay. So, let us try to prove this result. So, consider the term left hand side and with the square, and this is written by mod z. If I recall the property, mod z square is written by z into z bar now. Just by direct say applying the property, what we are getting, it is z1 bar plus z2 bar, and further you apply the distributive law, then we get that z1 multiplied by z1 bar plus z1 z2 bar plus z2 multiplied with the z1 bar plus z2 multiplied with the z2 bar, and we know that the quantity, this one is modulus of z1 square plus, here what we observe is z1 z2 bar treated as a one complex number, then the next number we are just seeing it as it is exactly the conjugation of previous one. So, if you just observe, so if I apply this bar, then it is z1 bar multiplied with z2 double bar, that gives again z2 itself. So, we see that this is mod z2 square, and we know that z plus z bar gives the real part of z multiplied by 2. So, we get that here it is 2 times of real part of z1 z2 bar plus this. Now, try to recall again what is the inequality we are trying to prove. Okay. We are trying to get the modulus of z1 plus z2 less than or equal to mod z1 plus mod z2. Now, we are seeing that almost we are reached here. If we are able to get something like right hand side as mod z1 plus mod z2 the whole square, then we are almost done, but only we need to see that how do we bring the term mod z1 and mod z2 here. Okay. So, if I recall the proposition which I wrote, that is the first one, it states that the real part of z always bigger than or equal to minus mod z as well as less than or equal to mod z. So, we are going to use this particular relation here. So, what we know is the real part is always less than or equal to. So, one need to be very careful about when we are using this relation, as I warned you that for complex numbers such a relation is not applicable. If you see the quantity above one, it is completely real numbers. Okay. Now, when we are comparing here, it is 2 times of modulus of z1 z2 bar, again it is a non negative number, and mod z2 square, and again what you see is that the property z1 mod z1 square plus 2 times of mod z1 multiplied by modulus of z2 bar, that is same as modulus z2 plus mod z2 the whole square, and we know that this is nothing but this is mod z1 plus mod z2 the whole square. Okay. Again what we derived is a square less than or equal to b square, that implies a is less than or equal to b. Okay. So, that proves our triangle inequality. So, I would like to point out that question one can ask, when this equality holds for this relation, that is when modulus of z1 plus z2 equal to modulus of z1, maybe the conclusion I will write it here, okay, or the next page. So, we just derived mod z1 z2 less than or equal to mod z1 plus mod z2. Now, question is when do I see the equality? So, when this will happen? Now, go back, when we derived this inequality, this is the place where we use the inequality relation. So, the equality appears if and only if real part of Z1 Z2 bar equal to modulus of Z1 Z2 bar. So, the equality appears, so the equality appears in the, let me call it as equation 1 provided real part of Z1 Z2 bar, this is equal to mod Z1 bar. Okay. This is equivalent to saying that Z1 is a t times of Z2 where t is a non-negative real number. So, let me again repeat, we proved this triangle inequality. Question is when the equality appears. We just observe that the equality appears if and only if Z1 and Z2 they are just like linearly dependent type, that is like constant times of Z2, you are having like Z1 is just the constant times of Z2. In that case we get the equality. Let us see further say other consequences from this triangle inequality. So, we just observed that modulus of, so let me just repeat this, we have this relation and from this we can derive that mod Z1 minus mod Z2 is less than or equal to this. How do we derive this? Just say let us call it as this is 1. So, consider mod Z1, we just add and subtract Z2, then apply 1, then by 1 we get mod Z1 is less than or equal to mod Z1 plus Z2, and further you get modulus of minus Z2, but we know that modulus of minus Z2 is again same as mod Z2. So, from this we get that mod Z1 minus mod Z2 less than or equal to modulus of Z1 plus Z2. Okay. Similarly, we can interchange the role of Z1 and Z2. So, in this case we get, so if I interchange the role, because Z1 and Z2 is arbitrary. So, you can just interchange the role of interchange Z1 and Z2, then we observe that this is Z2 minus mod Z1, that is less than or equal to modulus of Z1 plus Z2, and as a conclusion what we observe is this implies modulus of mod Z1 minus mod Z2, that is less than or equal to modulus of Z1 plus Z2. Okay. Now, one can ask question, is this plus is really necessary? Okay. Can I have here minus? True. Okay. You can have minus sign again. So, it may be here plus or minus, still this is greater than or equal to modulus of mod z1 minus mod z2. Similarly, this is less than or equal to modulus of z1 plus mod z2. So, here I see something more general from the triangle. So, we have triangle inequality, and now what we see is much more general inequality for this complex numbers. So, proposition 7, modulus of z inverse is mod z inverse, where z is a non-zero complex number. Again it is like similar to the conjugation property, we can derive this result, that is start with z inverse, that is z inverse is given by z into z inverse, you get identity, then its modulus, again modulus of 1 is 1, and we have already discussed modulus of z1 into z2 gives mod z1 multiplied by mod z2. So, what you get is mod z multiplied by modulus of 1 by z, this is equal to 1. So, what we observe is inverse. So, mod z inverse is exactly z inverse mod. So, this is the conclusion. So, what we see is that this implies that mod z inverse is nothing but modulus of z inverse, that is 1 by z. So, that is our proposition. And proposition 8, which is modulus of z1 by z2, which gives mod z1 by mod z2, you assume that z2 is non-zero. The result is again, say, just see as a product of two complex number, that is z1 multiplied by z2 inverse, then we see that modulus is applied for each factor, and the previous proposition we just proved that modulus of z2 inverse is same as mod z2 the whole inverse, and this is nothing but mod z1 by mod z2. Okay. Now, another interesting result which is called parallelogram law. It states that modulus of z1 z2 whole square plus modulus of z1 z2 z1 minus z2 whole square, which is same as 2 times of mod z1 square plus mod z2 square. Okay. Why they call it as parallelogram law? Let us try to observe this. So, let us call say the point as z1, and let us say that this is z2, and we know that the z1 plus z2, which is exactly gives the vector which is diagonal of this parallelogram, that is z1 plus z2, and similarly the other diagonal gives the z1 minus z2 vector. Now, if you see the identity, it says that square of the magnitude of this diagonals, consider its sum, that is equal to twice of magnitude square sum for the sides of the parallelogram law. Okay. So, this is very interesting property. So, and proof is simple, you need to just expand for the left hand side, then we can easily derive the, we can arrive to the right hand side. LHS, which is modulus of Z1 plus Z2 square plus Z1 minus Z2 the whole square. So, by definition this is Z1 plus Z2 multiplied with Z1 plus Z2 bar plus Z1 minus Z2 multiplied with Z1 minus Z2 the whole bar. So, the quantity what we are calculating is Z1 plus Z2 the whole square plus Z1 minus Z2 the whole square. This we written it as Z1 plus Z2 multiplied with Z1 bar Z2 bar plus Z1 Z2 multiplied with Z1 bar minus Z2 bar. By simplifying it, we see that this is Z1 into Z1 bar, that is mod Z1 square, and the other term which is mod Z2 square, and the remaining term what we have here, it is Z1 Z2 bar plus Z1 bar Z2. On this term we again get the term which is mod Z1 square and mod Z2 square. Remaining factors or comes with the opposite sign to these factors, that is minus Z1 Z2 bar minus Z1 bar Z2. Say these terms are cancel each other, then what we get is twice of mod Z1 square plus mod Z2 square. And let us discuss a problem which involves the modulus sign. Prove that if modulus of Z1 equal to 1 as well as modulus of Z2 is also equal to 1, and further their product is not equal to minus 1, then we can show that Z1 plus Z2 divided by 1 plus Z1 Z2 is a real number. Okay. So, let us try to observe this problem. What is given is Z1 Z2, they are basically on the unit distance from the origin, and their product is not equal to minus 1, then the quantity what we defined is a real number. It is really nice to see that the expression is looks complicated, but what we get at the end, it is a real number. Let us see how to show this. As I mentioned earlier, to say a complex number is a real number, just show that Z and Z bar it is equal, okay, which is same as saying that imaginary part is 0. Okay. So, let us define, like consider A to be the number Z1 plus Z2 by 1 plus Z1 product with Z2. So, our claim is A equal to A bar, that shows that the imaginary part is 0. So, now consider A bar. Now, the property whatever we have studied before, we are going to apply it. So, the conjugation for the whole factor. So, when we are having conjugation, for this which is Z1 bar, Z2 bar plus Z1 bar Z2 bar. Okay. Now, we need to relate Z1 bar to Z somehow. Okay. We have not used the condition modulus of Z1 equal to 1, similarly modulus of Z2 equal to 1. So, we need to use this condition. So, now let us say see that since mod Z equal to 1, so this is given to us, which is same as its square is 1, let us call it as the first number Z1 square. So, this is same as, this implies Z into Z bar is 1, and okay, we are able to get what is Z bar is. Z bar is Z inverse. Okay. So, by this relation we just obtained that Z bar is given by 1 by Z. So, we have fixed with the notation that we have considered the Z1 as our complex number. So, the Z1 bar as thus, similarly Z2 bar is 1 by Z2. Okay. Now, we need to just use this relation in the A bar. So, A bar is given by, we have Z1 bar that is replaced by 1 by Z1, and similarly Z2 bar is replaced by 1 by Z2, and 1 plus 1 by Z1 multiplied with 1 by Z2. By simplifying this expression, what we end up is Z1 plus Z2 divided by 1 plus Z1 multiplied with Z2, which is nothing but A. Okay. This implies A is a real number. Okay. So, let us just write a remark here or a comment. What we observed is mod Z equal to 1, then what we see is that Z into Z bar is 1, and Z bar can be written as 1 by Z. Okay. And just notice that again that modulus of Z bar is same as 1 by mod Z, that is again 1. Okay. So, let us maybe try to understand again about this, say all those Z complex number whose modulus is 1. Let us try to understand this. So, consider the unit circle as set U, which is defined as set of all complex numbers such that whose modulus is 1. Now, try to describe what are all the elements which is in this set. So, when we write mod Z equal to 1, this is precisely if we consider Z as x plus I y, then mod Z, which is square root of x square plus y square, if we consider its square, then it is x square plus y square, and it is given that mod Z equal to 1, then it is 1. Now, you ask what are all the pair of elements x y satisfies this equation, and which we are very familiar that it describes the unit circle with centered as origin. So, let us draw the picture. So, we have a unit circle, so any point on this, take the pair x y on the circle which satisfies this equation, and it means that the set U exactly describes this unit circle. Now, we know the points on this, for example 1 which lies on this and I which lies on this, minus 1 and minus I, they lie on this unit circle. The previous problem what we discussed, where mod z equal to 1, then we concluded that z bar is nothing but 1 by z, which is very easily seeable. Just this equation means that z into z bar equal to 1, z into z bar is nothing but mod z square equal to 1, that is holds because mod z is 1. So, let us try to visualize on this graph. When we take I, its conjugation is minus I, and this equation tells that z inverse is exactly its conjugation, which means that I inverse with respect to the complex product is nothing but its conjugation, that is minus I. If you take any element on this line, on this circle, consider its mirror image, that is exactly the conjugation. Consider any point on the circle z, consider its mirror image which is z bar, that is exactly the inverse of z, which is also lies on the circle. So, if you take 1, its mirror image itself, so inverse is 1 itself, and if you take minus 1, its mirror image again itself, so the inverse is just minus 1 with respect to the complex product. So, what are the observations we made here? Whenever we take two complex numbers on the unit circle, their product again in the unit circle, this is just simple property that modulus of z1 z2 is mod z1 mod z2, and each modulus is 1. So, their product is 1. And second important property which we observed, whenever z in U, z inverse is also in U, and not only that, this z1 z inverse is just the its conjugation of z. So, with this observation, let us prove a nice identity. Consider 4 complex numbers z1, z2, z3, z4 or complex numbers, then it satisfies the following equation: z1 minus z2 product with z3 minus z4 plus z1 minus z4 product with z2 minus z3, this is equal to z1 minus z3 product with z2 minus z4. Observe this identity, it can be any 4 complex number, then the following equation satisfied. Proof is simple, just expand the left hand side and the right hand side, then you will see that both expressions are equal. Let us consider the left hand side. Left hand side is the expression which is z1 minus z2, z3 minus z4 plus z1 minus z4 multiplied with z2 minus z3 Now just expand it, Z1 Z3 minus Z1 Z4 minus Z2 Z3 plus Z2 Z4 and further plus Z1 Z2 minus Z1 Z3 minus Z4 Z2 plus Z4 Z3. Okay. Now, we see that there are some common terms with they cancel each other, that is Z2 Z4 fine, maybe just let us go for the right hand side. Which is Z1 let us expand this Z1 Z2 minus Z1 Z4 minus Z3 Z2 plus Z3 Z4. Then we identify these two elements, and similarly Z3 and this we identified, and Z1 Z4 we identified, Z1 Z2 has been identified, and these two gets cancelled. So, what we verified is the left hand side equal to the right hand side. So, it is very interesting that it is a non trivial identity. You consider any 4 complex number, it satisfies this particular identity. Now, we can see a simple problem which demonstrate that how nice this identity is. Problem, suppose say we are given 4 points in a plane. So, show that if A, B, C, D are points in a plane, then the following inequality satisfies, that is AD multiplied with BC less than or equal to BD multiplied with CA plus CD plus multiplied with AB. Okay. So, let us try to say understand this particular inequality. So, let us try to draw a diagram, though the points can it be distributed in any manner. Okay. So, for the simplicity I am trying to assume something like they are not really lying in a line. In fact, let us say it basically gives some sort of shape. So, let us call it as this is A, B, C, D. Then this inequality says that you consider the length AD multiplied by the length BC, this will be always less than or equal to BD, the diagonal with the AC you multiply, plus CD multiplied with the AB. Okay. So, proof is, which is simple, just by using the previous identity. Let me just write down the identity. So, what we have, so what we can do is, once these points are kept in the plane, then we can identify each vertices or the endpoints to a complex number. So, let us say that this A is associated with the Z1 and this is basically associated to Z2, and C is associated to point Z3, and let us say that this is associated with the Z4. Then the previous identity says that Z1 minus Z4, Z2 minus Z3, that is equal to Z1 minus Z3, Z2 minus Z4 minus Z1 minus Z2 multiplied with Z3 minus Z4. So, I just rewritten in a way that I get the term the A to D, that is Z1 to Z4 and B to C, which is Z2 to Z3. When I take the absolute value for this identity, then the modulus of Z1 minus Z4, that gives the magnitude of this vector, that gives the length, that is the AD. So, now take the modulus sign to this identity, then the modulus of Z1 minus Z4 product with modulus of Z2 minus Z3, and now you have modulus of the entire term and apply the triangle inequality, we get that Z1 Z3 Z2 minus Z4 plus Z1 modulus of Z1 minus Z2 modulus of Z3 minus Z4. Okay. Now, we see that this describes the length of AD multiplied with Z2 minus Z3, that is length of BC, which is less than or equal to Z1 minus Z3, which is the length of AC multiplied by Z2 minus Z4, which is BD, plus Z1 minus Z2, which is AB multiplied with CD. Okay. So, we are able to derive the desired inequality using this identity. Now, let us do one more problem. So, before going to the problem, let me just mention that Z is said to be unimodular Z is said to be unimodular if mod Z is 1. Just a terminology, we say that a complex number is unimodular if modulus of Z is 1, which means the Z is lying on the unit circle. Problem. So, let Z1 Z2 be complex numbers and suppose the number Z1 minus Z2 divided by 2 minus Z1 Z2 bar is unimodular. And Z2 is not unimodular. Then we need to choose the one of the following choice. The point Z1 lies on a, it is lying on a straight line parallel to x axis. Option B, straight line parallel to y axis. Option C, whether it lies on a circle of radius 2. So, the meaning of this one, modulus of Z is whether Z1 is 2. Okay. d whether the circle of radius root 2. Okay. So, we are given that z1 minus 2 times of z2 divided by 2 minus z1 multiplied by z2 bar is unimodular, meaning is that the modulus of this number is 1 and modulus of z2 is not unimodular. Then we need to find out whether z1 lies in a straight line or a circle with a certain option that whether the radius is 2 or root 2 if at all lies in a circle. Let us try to derive what happens with the conditions to z1. So, let us try to see that the given point is modulus of z1 minus 2 z2 divided by 2 times 2 minus z1 z2 bar, modulus is 1 and modulus of z2 is not equal to 1. These are the given assumptions, and with the first assumption we can see that modulus of z1 minus 2 times of z2 square, which is same as modulus of 2 minus z1 z2 bar square, and we know that mod z square is same as z into z bar. We just write down that this implies z1 minus 2 z2 multiplied by z1 minus 2 z2 the bar, this is same as 2 minus z1 z2 bar multiplied by 2 minus z1 z2 bar the whole bar. So, this implies that z1 minus z1 minus 2 z2 and multiplied with z1 bar 2 times z2 bar, this is same as 2 minus z1 z2 bar 2 minus z1 bar and z2. And now just do the simple calculation. We see that this is mod z1 square and the other factor is 4 times of mod z2 square, and the remaining factor is minus z1 multiplied with this 2 times of z1 z2 bar and minus 2 times of z1 bar multiplied with z2. The right hand side, this is equal to 4 plus its mod square, that is mod z1 mod z2 bar square, does not matter because the modulus of z bar is again modulus of z. The remaining factors are minus 2 times of z1 bar z2 minus 2 times of z1 z2 bar. We see that these two factors are commonly appears, they cancel. So, we get the following equation that mod z1 square plus mod 4 times mod z2 square minus 4 minus z1 z2 bar the whole square, this is equal to 0. Now, we see that from this we can just say split this term as mod z1 multiplied by mod z1 square mod z2 square, then the common factor if we try to bring out mod z square z1 square 1 minus mod z2 square, and the remaining term which is if we take out minus 4 common, then 1 minus mod z2 square, this is equal to 0. Now, we can write it as a product term, okay, which is easily see that it comes that 1 minus mod z2 square multiplied with mod z1 square minus 4 equal to 0, and given assumption is mod z2 is not equal to 1, this immediately tells that this is a non-zero term, this is a non-zero term. So, immediately concludes that mod z1 square is 4 and mod z1 is 2, this immediately says that option C is correct. That is, mod z1 lies on the circle of radius 2. Okay. So, if I summarize, we discuss the more properties about modulus of complex numbers, and using the properties of conjugation of complex number together with the modulus of complex number, we derived certain problems, and in the next lecture we discuss about Argand plane and polar representation for complex numbers. Thank you.